So what I'm talking about is joint work with Anne Pichon. And so very quickly, let me just, I think everyone here knows about it, but I'll be working in the Lipschitz category all the time. So this is metric spaces, the objects are metric spaces, and the morphisms are Lipschitz maps. And then a Lipschitz map which has a Lipschitz inverse is by Lipschitz, so the isomorphism concept is by Lipschitz maps. And I'm interested in complex surfaces, but quite generally, if you have a complex germ, you can embed it always into some Cn0, and then it inherits geometry simply from the Hermitian geometry of Cn. So we have a metric which we call the outer metric, which for a pair of points x, y is just the distance in Cn between those points. But we also, from the outer metric, one can derive the inner metric. The inner metric is a weaker matrix where the distance between 2 points is the minimal arc length of a path in X from X to Y. And the outer metric is what I'll be talking about most, but I'll need to mention the inner metric along the way. So I mention them both. In the Lipschitz category, these are completely canonical, and they don't depend on the embedding. If you change the embedding, you have the same metrics up to by Lipschitz equivalence. So what I'm interested in is if you have such a germ and you know its outer geometry, what can you say about the best embeddings into Cn? How can you embed it into Cn? And let me start with the very simplest case where you actually have a curve germ. So a curve germ, I'm looking at something one-dimensional. Okay. So let me take a simple example of this. Let's look at a plane curve given, for instance, by y is equal to x to the 4 over 3 plus 9 over, what am I doing? I want to do 9 over 6, yeah. X to the 9 over 6, for instance. So this is a curve, a plane curve. You can sketch it. Roughly, it's got multiplicity 6, so if you draw the curve, it's hard to draw it in just 3 dimensions because it keeps on crossing itself, but it goes, if you intersect with a sphere so that you just have the knot given by the link, this is a knot with a total of 6 strands, and it lies, its tangent cone is one plane, and then we take an orthogonal plane. We take the y plane orthogonal to the x plane, and I'm going to the y plane intersecting the x plane intersects in one point. But then when we look at how it intersects the curve, we see it intersecting in this particular case in I hope I'm getting the numbers right. I think I've probably done it wrong. I think it's 2 bunches of 3 points or maybe 3 bunches of 2 points. I'm not sure whether I'm starting off, yeah, it's 3 bunches of 2 points, sorry. I've got 3 bunches of 2 points. And I can look at the distances between them, and if I look at how far I am from the origin here, R, I see that let's give these points names, P1, P2, P3, P4, P5, and P6. And what I see is that the distance between Pi and Pj is contained in the set. It's either of the order r to the 4/3 or of the order r to the 9/6 up to higher order. So we get points in pairs which are r to the 4/3 apart, points that are the closer points which are r to the 9/6 apart. So I have this collection of rates that at distance r from the origin, I have distances between the points being either distance to the 4/3 or distance from the 9/6. And it turns out that these numbers are enough now. These numbers are telling you the Poisson exponents and therefore tell you what curve you have. And so what we have is, in this particular case, we have that the numbers, the combinatorics, tell us the curve, so the embedded curve. This is determined on the one hand by the combinatorics, by the collection of numbers that we have describing the curve. And on the other hand, what we see is that these distances are really describing the outer geometry. It's telling us exactly what the outer geometry looks like. And so in this case, we have that if we know the topology, if we know the combinatorics, then we know the outer geometry and we know exactly how it's embedded too. So everything about the curve determines the embedding into C2. And in fact, this is originally Pham and Teissier, this fact that the geometry determines the topology, etc. And Teissier proved also that even if you have a space curve, you take a space curve, you look at the combinatorics of the distance, or you look at its outer geometry, then it can be embedded. That space curve does embed into C2, and that embedding into C2, the topology of it is unique. So for curves, even for space curves, the outer geometry determines the embedding completely. So dimension 1 is nice. Things behave very nicely, and the question is, what about dimension 2? So in dimension 2, I'm going to just look at normal. Here, of course, we didn't have a normal curve germ. If it were normal, it would be smooth and uninteresting. But in dimension 2, I'm going to restrict to a normal surface germ. And then we can ask basically the same questions. So first of all, here we could always take, given the geometry, we could always embed into C2, it turned out. So the first question is, given the geometry of the surface germ, what dimension can it embed in? What its possible embedding dimensions. Now, if the embedding dimension is high, then basically the topology is determined by the geometry. So the interesting case for us is going to be what happens if it's a hypersurface, what happens if it embeds into, can embed into X3, so into C3, and in that case we ask, so if X2, 0, just as a geometric object embeds, if it has an analytic structure so that it embeds in C3, what are the possible embeddings? Can it have more than one embedding topologically? So let me immediately give the answer. So, and then discuss it further. So the basic theorem is that there exist two hypersurface germs. Let me call them X1 and X2 with the same outer geometry but inequivalent embeddings into C3. So the nice behavior we saw in dimension 1 already fails.
This is inequivalent in the sense.
Pardon? Inequivalent, topologically inequivalent. There's no mapping, no topological mapping of the germs C30 to C30 taking X1 to X2. They're distinguished, in fact, by the algebraic topology of their complements. So I want to describe the example next. So to describe the example, let me remind you of superisolated singularities. So these are Luengo's super-isolated singularities. I'll just abbreviate to SIS. So this is Luengo 1987. So what this is you have a hypersurface given by an equation f of x, y, z equal to 0, where this f of x, y, z consists of a homogeneous polynomial of degree d, which is whose zeros so the zero set of this should be reduced. So let me write the c equal to f of d x, y, z equal to 0 should be reduced. And we look at this, since this is homogeneous, I'm going to think of this as a projective curve in CP2. So I have a curve described by this, and then one takes a homogeneous part of degree d plus 1, and with the requirement that the intersection of the curve given by fd plus 1 and the curve given by this curve c should only intersect c in smooth points. So fd plus 1 equal to 0 intersects c in smooth points. So this is the setup for a superisolated singularity. They're very beautiful singularities that have been used for many, many different counterexamples, including several counterexamples to conjectures of myself and Johnny Wall. So they've broken a lot of things. And so it turns out they're very nice. The topology of these are determined completely by the topology of this projective curve. And moreover, if you blow up once, so you've got your, let me give this f equal to 0 a name. So I'll call it x0. So I've got x0 inside of C30. If I blow up the origin of C30, so I do a single blow up and I take the pullback here, x tilde 0. This has already resolved the singularity. X tilde is now smooth, and the let me call the projection here pi inverse of 0 sitting inside here is simply isomorphic to this C. So the exceptional divisor is the curve C here, and we've got a nice smooth blow up. So these are the examples that we'll look at. And the examples I'm going to use are going to be two curves of the same combinatorial type, but different embeddings in CP2, so-called Zariski pairs. So let me just briefly say what combinatorial type is. So we say that two curves C and C prime in P2 have the same combinatorial type. And one way is basically by counting all the invariants, looking what singularities these curves have, what singularities, how many singularities of what type, genus of the curve, and so on. But there's a much more elegant way of saying this, which was mentioned in Matthew's talk, which is that you simply take a tubular neighborhood of C and a tubular neighborhood of C prime, and if these are homeomorphic, then one says that C and C prime are the same combinatorial type. And the examples I'm going to use to construct the counterexamples of the theorem are going to be the classical Zariski pairs which I'll call, let me follow what I said, I called them in my notes. I call them C1 and C2. Zariski called them C and C prime, C1 and C. And one of these is very easy to describe. Both of them are fairly simple. They're sextics. These are both of them sextics with six cusps, with exactly six cusps and no other singularities. And an easy way of describing C1 is you take two different curves. You take a quadric in C2 and you take a cubic in C2, intersecting them. So your quadric is given by an equation, let's say A of x, y, z is equal to 2, so homogeneous of degree 2. The cubic is given by an equation, what am I saying? A of x, y, z is of degree 2. B is given by a cubic equation, so of degree 3. We assume that they're nicely in general positions, so they're intersecting in 6 points. And then we look at the equation that we are interested in as a degree 6 equation. We take a cubed plus b squared as a degree 6 equation. And it's easy to check that this gives you something which has cusps at each of these points. A degree 6 equation with exactly 6 cusps and otherwise nicely smooth. So here is our, I should have had color here, but anyway, here is our C, which is the degree 6 curve. This is the C1, in fact. It's a degree 6 curve with exactly 6 cusps, nicely sitting on a quadric. And in fact, every curve, every degree 6 curve, which has exactly 6 cusps lying on a quadric, is given by this construction of the. And they form, in fact, as you vary them, they form a very nice equisingular family, Zariski equisingular family of such singularities. And then the other one, so we've got a C2. This is much more complicated to describe, and I won't describe it. It's simply another sextic, which also has exactly 6 cusps, but where the cusps don't lie on a quadric. Okay. And it took Zariski, I think, 5 years from conjecturing that this existed to actually proving that it existed to see that there was such a thing. So this is, C1 was, I think, in 1924, and this was 1929. C2, 6 cusps, not on a quadric. And again, a sextic. So these are the 2 examples that will be. Is it coming? Yeah. Well, let me move over to the right board for the moment. Well, let me just. So I've described what a superisolated singularity is. So now then we look at the superisolated singularities determined by these 2 particular curves. So we'll denote by x1 the superisolated singularity for C1. X2 is going to be the superisolated singularity for C2. Of course, there's a lot of choice. We've chosen the curve, but then we have the degree 7 extra term which constructs the super-isolated singularity for us, but they have the same topology, in fact, the same outer geometry, so we just make a choice and choose a super-isolated singularity for those two. And the theorem then is that these give our counterexample. So the way these are distinguished, this was a result of Artel proving that these are in fact x1 and x2 are distinguished by the Alexander polynomial, which is an invariant due to Libgauber. Namely, for x1, you have an Alexander polynomial which is t squared minus t plus 1, I believe it was, yes. T squared minus t plus 1. And the Alexander polynomial for x2 is simply 1. So you have an algebraic topological distinction.
These are the polynomials of the curves, not of the... So this is the Alexander polynomial of C1 and C2.
Okay, yes, of C1 and C2. But you prove that these also distinguish the super... Yes, thank you. Yeah, the point is that Libgauber gives the Alexander polynomial of the curve inside of P2, and Artel proves that those Alexander polynomials survive into the super-isolated singularities and distinguish them. And in fact, these are distinguished, at this point they're distinguished, the complement of these two curves are very radically distinguished also by the complement of their fundamental groups. C1, for instance, the fundamental group of P2 minus C1, this is actually isomorphic to PSL2Z, a nice big infinite group, which is, you could also think of as the free product of cyclic group of order 2 and cyclic group of order 3, while the other curve, C2, has a much simpler fundamental group. It's simply the cyclic group of order 6. And the question that I'd meant to ask you before the talk, so I can ask you now, to what extent does one see the fundamental groups in the system? Okay, I don't know either. Yeah. But anyway, the Alexander polynomial does it. So we're almost there with the proof of the theorem. We have these two, x1 and x2. They look very similar from a topological point of view, but they are distinguished. And what we need to see is, the last thing to see is whether they have the same outer geometry. So let me state two theorems. That was theorem 1, I guess, so this is now theorem 2. So suppose I have any two curves, now C1 and C2, no longer those two curves, but any two curves in complex projective space, CP2, with the same combinatorics. And x1 and x2 corresponding super-isolated singularities. Our first theorem is that then x1 and x2 have the same geometry, but this is inner geometry at this point. So the combinatorial type always determines the inner geometry of the corresponding superisolated singularity. And theorem 3, which is what we really wanted, we wanted that the outer geometry is determined if C1 and C2 are two curves with the same combinatorics and only cusps. They can be higher cusps as well as just the 2-3 cusps, but only cusps. Then, in fact, you can improve this to outer geometry, to the stronger geometry. So this, of course, is theorem 3, then proves theorem 1. Answers our So I'd now like to describe how one understands the geometry. How can one decide that two things have the same inner geometry or the same outer geometry? So let me start off by talking a little bit about inner geometry. So to be able to say that two things have the same geometry, we'd like some sort of a classification. So the classification of inner geometry of normal surface germs. So this is a result of Beer-Breyer. I always forget which way the I and the A go. Beer-Breyer. I think the other way. Thank you. Neumann. So this is in ACTA 2014, which describes a classification in terms of a decomposition into pieces. So let me state it as a theorem which is initially not quite correct, and then I'll refine it to make it more correct. But the basic idea is that given x0, is a canonical decomposition into semi-algebraic germs. So x0 is going to be the union of pieces xi0, I equals 1 to somewhere or other. And let me first of all draw a rough picture of this. So I have my singularity with the nice picture that Bernard drew for us. So something like this, scaling down towards the origin. Okay. And we have a decomposition into pieces. For instance, here we might have two pieces. And the basic thing is that we have a large zone which basically shrinks conically, which is why I've drawn the whole thing looking like looking like something conical. So there's a large region which just scales conically down towards the origin, and then I have regions which shrink faster than linearly towards the origin. So here I have pieces that are shrinking much faster than, and here enveloping them is something that's also shrinking faster, but not quite so fast towards the origin. So what I have, I have pieces which, as I said, they're shrinking at certain rates towards the origin, so each xi has a rate qi, which is a rational number greater than or equal to 1, there is always something completely conical in what we're looking at. So there are pieces, so qi equal to 1 does occur. It could be that the whole of x is metrically conical, in which case you just have one piece. But otherwise, if you have other rates, we have the rates associated to the pieces, and the other thing is that adjacent pieces always have different rates. And in fact, as you move further away from where things are metrically conical, the rates are getting larger. In other words, the rate of shrink is getting smaller. So you have these pieces glued together like this. Have I said what I... Yes. And let me say how these pieces shrink, because that's important. So each of these pieces is a full dimension, and they're being glued together along boundaries. And if qi is equal to 1, we've just got some big amorphous piece that's shrinking conically towards the origin. But the pieces that have qi greater than 1, which are shrinking faster than conically towards the origin, their general picture, their geometry, looks like basically a fiber bundle over a disk. Topologically, here we've got the origin. So here we've got a plane, two-dimensional, and we've got a bundle which has little complex curves as fibers over this, and it's these fibers, they're actually parts of Milnor fibers of the general linear projection of x to the plane. These are what's shrinking actually at whatever the given rate is. So that's how the rate of shrink comes about. So we have, very schematically, we've got something that is over a disk. It's got something that's shrinking down in a kind of wedge shape. And if you think about it, if I have two pieces with different rates next to each other, there's no way I can glue them together. If I've got another piece which is shrinking much faster, there'll be a gap between them. And so what I said over here of simply gluing pieces together has to be wrong. You have to mediate between the two pieces to make things work. And so what one actually has to do is we glue in extra annular pieces. I'll call them AJ pieces, which basically look like what I drew. The boundary components here are tori. So we've got toral annuli over a circle here. We've got an annulus. This circle, as we go around the disk, becomes a torus. And we're having to glue in these toral annuli with different rates of shrink on the two boundaries to actually mediate between them. But this then gives us a complete classification of the inner geometry. Namely, given x, there's a minimal such decomposition. We've got algebraic topology basically tells us where these vibrations are, so further discrete data on how to decompose it, and the QIs are discrete data. So we've got discrete data from which we can recover all of the algebraic geometry of this. Now then, the outer geometry, we haven't actually yet written down a full classification, but it's basically the same idea, but one has to refine this decomposition a bit, because there are pieces where X has a lot of curvature that you pick up through the outer geometry. You have places where parts of X are distant in the inner geometry from other parts of X, but close in the outer geometry, if you've got two sheets kind of in a covering space. So we have to add extra data, but again, discrete data to give the outer geometry as well. And I think the best way to describe that quickly is simply to give to show you what it looks like in our nice example. I lost my... So we'll look at the Zariski example. So what does the Zariski example look like? We have these cusps. We have the 6 cusps giving us the thin zone. So they're kind of 6 little, I'll draw them very schematically as 6 thin zones and a big fat thick zone. And each of these thin zones, let me draw the resolution graph. The resolution graph, for those who like resolution graphs, it's a very helpful way to seeing the picture. We have a central curve. We have the cusps give us 6 things like this. 1, 2, 3, 4, 5, 6. I won't draw in all the numbers, but we've got symmetry like this. And I didn't actually put it in my notes, so I think this is minus 42, but I'm not sure. Anyway, there's some Euler number in the middle. Is that right? Yes. And so we're seeing in the resolution what look like the original cusps, and here minus 42. So I want to describe what these thin zones look like, and as I said, the thin zones we can describe in terms of this fibration over a disk. I should say that the multiplicity at the central point is 1. If it were higher, this disk itself would be, if you had higher multiplicity, the disk actually with its outer geometry would be a branched cover of a disk, and you'd have some interesting outer geometry here. But the multiplicity here is 1, so it's really basically a nice flat disk over which we have these pieces which are telling us what the geometry looks like. So those pieces are fibered over such a disk, and I want to say what the fiber is. The fiber is simply a punctured torus. And what we have is a rate of shrink, an overall rate of shrink of this punctured torus. So the inner geometry, basically, for this punctured torus is very simple. It's simply 4 over 3. There's no further decomposition of this, and the QI is 4 over 3. So if you were just looking at inner geometry, this would have described the complete inner geometry of the object we're looking at. But now for the outer geometry, we take account of the polars of projections. So those are regions where you have a lot of curvature, more curvature. And there we have 3 such regions. And those regions shrink at a rate of 5 over 3. So their rates are all 5 over 3. And the way this object actually arises is as a double-branched cover over 3 disks. So because these are the polars, you've got a covering from here to here. This double-branched covering of a disk at 3 points gives you a punctured torus. And so what that means is we have 2 sheets close together here, and we have to talk about the outer geometry of those 2 sheets. And the outer geometry of those 2 sheets is, let me kind of draw it schematically as distance between sheets. That's given by a rate of 3/2. So here we have the data that fully describes the outer geometry. And this is true. You see this same geometry anytime you have a super-isolated singularity where the curve is just based on cusps. So that's basically the way we distinguish, the way we see that the C1 coming from, or the X1 coming from the Zariski, the X1 and the X2 coming from the Zariski pair, they both have the same. Here's a complete description of their geometry, and they both have the same. So, yeah, so basically, I could stop there, but let me just briefly say that in the last 3 or 4 minutes, let me just briefly say that this outer geometry here, the outer geometry, even though it's not determining the embedding, it does determine a huge amount of information about a surface germ. So let me just finish by mentioning very briefly, this is the outer geometry of a surface germ. We hoped that it would determine the embedding, but it doesn't determine the embedding. But it determines, for instance, the multiplicity. It determines the topology of the pair X and the intersection with a general hyperplane. So it completely determines the topology of this. It determines analogously, the topology of X and X intersected with the polar of a generic projection to C2. It also determines completely the resolution of these triples. So you can get a complete resolution of the X resolving also X intersection H and X intersection pi and how those fit together. And finally, if we look at the projection to C2, so then we have C2 and the image of pi, which is the discriminant. It determines the discriminant in C2. And what this in particular implies is that if you have a family of isolated surface germs. No, this is completely general now. This is any normal surface germ. All of these are determined. And in particular, if we have a family of surface germs with constant outer geometry, then this is saying that we also have constant topology of the discriminant. And constant topology of the discriminant is equivalent to every sort of equisingularity in dimension 2. So we for curves in dimension 2. So here we see that if we have a family, we get equisingularity 1 dimension 2. But Zariski defined equisingularity by saying that if you have a family in 1 dimension, it is equisingularity if it is equisingular if in the projection you have equisingularity. So in particular, one gets the result that any family which is Lipschitz continuous is actually Zariski equisingularity. And let me stop there. Thank you.
Thank you. Are there any questions? Yes, you need to speak into this.
So in that case, when you say cusp, you mean ordinary cusp or any kind of locally reducible singularities? In theorem 3.
In theorem 3, they can be any cusps, in fact.
Any
but
cusp.
It's when you have more than one Poiseuille pair that we believe that there are counterexamples, but we haven't checked that carefully. Okay.
And in this determination, so have you studied the characteristic polynomial of the monodromy, if it's also determined? Because, for example, in the combinatorics in the superisolated case also determines the characteristic polynomial of the monodromy.
Yeah, no, we haven't thought about that. Very nice question. Thank you.
Other questions or comments? Very.
So your result is saying that if we have a family of surfaces with constant outer geometry, then since there's risky equisingular, the family is embedded topologically trivial?
The family is, yes.
So what goes wrong is those invariants which don't change continuously then. Is that the invariants you use to distinguish between the two germs originally, there must be some drastic change if you try to move one germ to another.
Yeah, there's a nice example, for instance, one of the, what's the name? The ones who have all the examples. Brianson-Spader. There's a nice Brianson-Spader example, x cubed plus x to the 4th y plus y to the 6th plus c to the 6th, where you actually have constant inner geometry in this. I've got a t in front of here. It's parameterized by t. You have constant inner geometry for this family, but the outer geometry changes and therefore other invariants change. In fact, this is a mu constant family, but not mu star constant. I think that's right, but it's certainly, there are other numerical invariants which change. For instance, the number of components of the polar here is 12 when t is not equal to 0 and 6 when t is 0. You have crossing lines degenerating into cusps.
Anybody else? Yes.
Are your two surfaces topologically equivalent in some higher dimension? Can you embed them in C4 in such a way that they are topologically equivalent?
I believe the answer is going to be yes, but I don't know. I've thought a little about that, but I don't have a...
Anybody else? In that case, we'll thank the speaker again.